In Lesson 7.2, we looked at ways of showing data in an organized manner that makes the data easy to understand. But we didn't see examples of bar graphs that were horizontal. And I wanted you to look at this bar graph representing Florida beaches, where it gives the names of the counties, and then it gives the amount of sand used in millions of cubic yards written horizontally. So that is an acceptable way of showing a bar graph. When you're working with students and trying to get data that the students can work with on their level, one teacher in the second grade decided that she would have the students get out pencils and crayons and put them on their desk with no prompting as to how many to get of each type. And once they got out what they wanted, she then had them count. How many pencils do you have? How many crayons do you have? And then they created a frequency table, and from that frequency table were then able to do a line plot. So the students could see that most of the students picked out 2 pencils, one picked out 9 pencils. And so you could see that this is unusual. So you're beginning to see examples of what we consider to be an outlier, or data that is not the typical. So we could say that most students had 1, 2, or 3 pencils. Another way that the students might take that and represent it would be as a bar graph. But study shows that the students are able to read a bar graph, but they are not able to analyze it. And so asking leading questions in order to help them analyze what the graph looks like or what the graph is telling them is very important. How many is a lot of pencils? Do you have a lot? What is the greatest number of crayons one person had? What's the fewest? What is the most common number of pencils that a student had? And so by asking those leading questions, not only are they able to recognize and use a bar graph, but they're able to analyze the situation. Another way that you can have students get some data is by having them simulate that they are jumping across a creek. And so you ask, can you jump across the creek? So you give some amount that you think is acceptable for the distance across a creek. And then you set up the scenario where you have your tape measure and you have the students jump, and then you might give them a table where they have an estimate as to how far do you think you can jump, and then they get 3 tries in order to do that. When finished, they can put their measures onto a bar graph, or this is a histogram because it has the frequency, and then the bars are next to each other. Another way of gathering data is to have the students stand first on their dominant leg, which would be, if they're right-handed, their dominant leg is their right leg, and they could have 2 or 3 tries in order to get their maximum. And then they would stand on their non-dominant leg. They could organize their information into a table, and they could make inferences. By trying 3 times, did my time increase on the dominant foot? Or after the 3rd try, was I tired and did my time decrease? And then on the non-dominant foot, the same. And then they can compare to each other. So they have not only the comparison within one foot, but then they have the comparison between the dominant and non-dominant. Then they can put their information together as a class and create the bar graph for the length of time in seconds that they could stand on one foot. So, simple ways of putting together scenarios where students can actually gather data and organize it into meaningful graphs. In 7.2, we're going to begin looking at ways of collecting and describing and analyzing. Statistics is said to be the science of collecting data and making inferences. Descriptive statistics, which is what we're going to do, is the science of collecting, describing, and analyzing. And then inferential statistics, which we will look at later, is the science of interpreting data in order to make predictions. One way of looking at our data is to try to see where the center of it is. And that's what the measure of central tendency does. There are 3 terms that we deal with central tendency. One is the median, where you find the average. One is the mean, where you find the average. One is the median, where you find the middle after you order by size. And the last is the mode, and that's the number that appears most often. And you can have more than one mode. You can have 2, you can have 3, but it is the number or numbers that appear most often. Alright, let's look at some data. Let's look at 64, 14, 23, 43, 39, 17, 8, 14, and 18. If I want to analyze the middle of the data, I can look for the mean. The mean is sometimes written as X bar. I would add and I get a sum of 240. Sometimes we use sigma to represent sum. If I find the sum of all x values and I divide by the number of values that I have, 2, 4, 6, 8, 9, I get the mean. If I want to find the median, I have to order the numbers by size. So I'll start with 8, 14, 17. Oops, I have another 14. I have two 14s. I have an 18, a 23, a 43, 39, and 64. So I order these by size, and I find the middle. If there's an odd number, it's easy to get the middle. There will be 4 above and there will be 4 below when I have 9. So the median is 18. The mode is the number that appears most often, and out of this group there is only one mode, and that is 14 because it appears twice. We want to give students the opportunity to compare the mean and the median, because there are times that it would be to our advantage to use the median as opposed to the mean. So let me show you an example of where that would be the case. Let's say that you are interested in buying a home, and we have a home for $125,000. We have a home for $130,000. We have a home for $128,000. We have a home for $110,000. And then we have a home that's in this housing development that is a $500,000 home. If we take the average value of the homes, so we'll add those up. I get a sum of $993,000. I want to divide that by 5. And the mean is $198,600. So you can see that the mean is greater than 80% of the homes in that housing development. So by having this unusual value, it makes it look like the homes are more valuable in that subdivision than they actually are. So in this case, using the mean would not be as good an estimate of the value of the homes as the median would be, because when I order these by size, I have 128,000, which is a better representation of the homes than 198,000. This represents about 80% of the homes, whereas this does not. So the median often is a better representation. Often when you hear about the income for a state teachers, the Kentucky teacher income, they give you the median instead of giving you the average. Another concept of mean that I want to speak to you about, and I get this a lot just when it gets to be grade time. I might have a student come to me with an 88%, and I've given 4 100-point tests. They might say, if you give one more test and I make 100 on it, would that give me an A? So if I know the average to be 88 on 4 tests, that means that the person would have 352 points out of 400. If I add another 100 points to the person's score and another 100 points to the points possible, will that give the person an A? So 500 won't go. I add a 0. And you can see that by giving one more test, if the student got perfect, that would bring them up to an A. But when you're trying to see what a number will do to the mean, you have to go back to the original amount of points that you had and the original amount of points that was possible. So you take the average times 4 and then add on the extra value and then recalculate. So mean, median, and mode are the numbers that deal with measures of central tendency. According to the National Council of Teachers of Mathematics standards, students need to understand that the mean evens out or balances a set of data, and that the median identifies the middle. And the student should be given opportunities to show the comparison of what the mean and median does to data. The next way that we want to represent data is by looking at a box and whiskers plot. And the data is divided into 4 categories in a box and whiskers. You have the minimum and the maximum. You have the median. You have quartile 1 and quartile 3. So let's look at some data. Alright, so we have some data values. I need to know the median. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, if I have an even number, there is no middle. So I have to average the 2 numbers that are in the middle to get the median. But first of all, I have to be sure that these numbers are in order. So I have 30, 32, 33, 35, 35, 35, 37, 38, 38, and 39. So there are my 10 numbers. 1, 2, 3, 4, 5. The 5th and the 6th numbers would be the middle. You have 4 above, you have 4 below. Well, these are the same, so I was lucky. So the median is 35. You average the 2, so the median now is here between the 5th and the 6th. Now I have these 5 numbers, and I want to find the median of those 5. Well, the middle of 5 is 33, so that's quartile 1. And then I'll find the middle of these 5, which is 38, so that's quartile 3. So I find the median, and then I find the median of the top half, and then I find the median of the bottom half, and that makes 4 categories. I make a number line, and I'm dealing with the numbers 30 to 39, so I have the numbers 30 through 39 on the number line. The minimum was 30, so I'm going to make a dot. Quartile 1 is at 33, so I'll make a dot. The median is at 35, so I make a dot. Quartile 3 is at 38, and I make a dot. And then 39 is the max, and I make a dot. At quartile 1, I'll make a segment and a rectangle all the way to quartile 3. So I'm making a rectangle from quartile 1 to quartile 3. Half of the data values fall in this rectangle. Half of the data values fall between 33 and 38. I put a line where the median is, and I connect with a segment from the minimum up to quartile 1 and a segment from quartile 3 to the max. Now notice that the line from quartile 1 to the min is a lot longer than the line from quartile 3 to the max. So that means that 75% of the data is above 33. And that the data is closely clustered around 33 to 39. And it's spread more here on the lower quartile is spread more. Now, a nice thing about the box plot is that it lets us see the numbers that are far away from the middle. And it will allow us to get suspicious about what might be an outlier or what might be abnormal. So we have a rule, and that is to take quartile 3 minus quartile 1. And that's called the interquartile range. If I multiply the interquartile range by 1.5, that will give me a value to take away from quartile 1 and to add on to quartile 3. So if I have values that are below the number I get for quartile 1 minus 7 5/10, I would have an outlier. If I have a number above quartile 3 plus 7 5/10, I have an outlier. So I'm going to take quartile 3, which is 33, minus 7 5/10. And I get 25 5/10. Well, I had no numbers below 30, so I have no outliers in the lower region. If I take quartile 3, which was 38, and add 7 5/10, I get 45 5/10. And I had no number above 39, therefore there are no outliers in this set of data. Alright, again, the interquartile range is used to help find outliers. And we take quartile 3 minus quartile 1, then we multiply that by 1 5/10. We add it on to quartile 3, and we take it away from quartile 1. And then if we have data values that are above or below, then we have an outlier. Alright, I want to show you some examples of box and whisker plots, and we'll analyze some of these. This represents speed in miles per hour, and notice that the whiskers in the upper quartile is about the same length as the whiskers in the lower quartile, and that the box, which represents 50% of the data, shows a median about in the middle. So this data is spread relatively evenly. In the next box plot, notice that this whisker is much longer, so it would make you suspicious that possibly this would be an outlier. Now this is about home runs, and so it looks like there's about 46 home runs was a max, and then the min was 0 home runs, and about 50% of the data fell within 10 to 24 home runs. So let's look at this to see if possibly 46 is an outlier for this set of data. Quartile 1 is 10. Quartile 3, I think, probably is about 23. So the interquartile range is 13. So I'll multiply that by 1 5/10. And I get 19 5/10. I will add that on to quartile 3, and I will take it away from quartile 1, and that's going to give me a negative value. And in looking at the home runs, 0 was a min. I had no negative home runs. Therefore, there are no outliers on the lower end. On the upper end, however, remember that 42 5/10 was the value, and you can see that 46 is above that. Therefore, values that were above 42 5/10 would be considered outliers. So we know we have at least one, which was the max. The box and whisker plot does not maintain the original data like the line plot does, but it gives us how the data is spread. We can compare using two box plots. This is showing temperature in January and temperature in July. And so on the number line, we can see that about half of the days in July, our temperature ranged from 75 to 88. And about half of the days in January, our temperature ranged from about 28 degrees to 40 degrees. It looks like that the whisker is pretty long here, up to 62 degrees. So it looks like there might be a possible outlier. and look how closely 75% of the temperatures in July were above 78 degrees. So the 60 degrees is pretty low. So it also might be an outlier. And we would use the interquartile range to check to see if that is so. In 7.2 Part 2 lecture, we will be talking about how data varies, and I'll be showing you how to use your calculator in order to find the mean and the median and the standard deviation.